Okay, so remember that we looked at, toward the beginning of the semester, we looked at given where y is a function of x. And we looked at that the area, or the difference of areas from that function to the x-axis. We saw that the integral was one application of integral, say from x1 to x2. Where this was like the area of a really thin rectangle, right? We said this was kind of this although it is an application of integrals, we said it was like kind of a superficial, right? Because the real meaning of integral would be the total change or total amount of a quantity whose rate of change was f. But then because we graph in rectangular coordinates, it could also be, integrals could also be used to find areas based on rectangles, right? And so what about, how can we apply that area idea here to parametric graphs? So basically this is y, right? F of x is y. So in parametric we have x is some function of t. So I'll just call it p of t. And y is another function of t called q of t. Because I already used f. So then what would y dx be if we were to get this into our with respect to our parameter t? So what is y? What is y equal to? Q of t, right? So this is the y is q of t. And what is dx? If x is p of t, then what is dx? Yeah, so the derivative, so it'd be p prime of t dt. So there, we just changed it from x, from a variable x to variable t, but it's doing the same thing. It's still calculating vertical rectangles to the x-axis because it's equivalent to this, right? This is our thin vertical rectangles between the curve and the x-axis, and so we're just making that thing equivalent in t. So that would be our function of y times our function of x, the derivative, our function of x dt. All right, and then it would just be from the starting value of t to the ending value of t. And the area that you find is going to be that's going to be though an x-coordinate, right? So it's going to be whatever the area will be defined by whatever x-coordinate you start at t1 and whatever x-coordinate you finish at t2. Okay, so if we just look at, say, from t equals 1, let's look on this curve. Let's say if we wanted to find what this integral would represent. So if we did the integral from, for this function here, if we did the integral from negative 1 to 1.45. This is t equals negative 1 to t equals 1.45. Of this thing, q of t, p prime of t dt. So what would that represent? So let's take a look at t equals -1. So it looks like at t equals -1, it's x equals -3. I'm guessing, yeah, I'm guessing that at t equals -1, let's see if that's right. So we'd have -1 minus 3 plus 1, yeah, so -3. So here's t equals -1. We have the point, what, -3, 6. Okay, so there's that right there. And then 1.45. So I think 1.45 is, yeah, it's basically that root right there. So here is t equals 1.45. -2.26, comma 0. So what would we get? What would it represent if we did this integral here, starting at from t equals -1 to t equals 1.45? What area or areas would it represent? Well, we're graphing all ordered pairs x, y, right? We're graphing all ordered pairs x, y here. Okay, so it's like I said, it's still, this formula is still based on what? Vertical rectangles, you know, between the curve and the x-axis. So if we think about starting here, and now the curve, the direction of the curve is this way. So when as t increases from -1, we go this way. So let's kind of break this up. We have this rightmost point where t equals 0. There it is. So we can think about this as the integral from -1 to 0 of, you know, q times p prime dt plus the integral from -1 to 0 to 1.45. So what would this give? So if we went from -1 to 0, -1 to 0, and again, this is essentially y dx. This is y dx. So can you see what area that would give from -1 to 0? Yes. Tell me. Explain it.
It'd be the area under the graph from the leftmost point
Uh-huh.
to the rightmost point.
So by this is the leftmost point?
Yeah.
Yeah, so if we dropped let me do this a little better than trying to draw that. What is y value is that? Or x value is -3? So let's do x equals -3. Okay? And then,
To the rightmost.
which is x equals what? Point for that? 1, yeah. See if this shows up. Maybe not. Do those show up? Perfect, just a little bit light. Okay, so it's going to be, yeah, it's going to be the area under that curve that's like sloping down to the right, down to the x-axis. So I'll shade that here. So it's going to be like all of this. That would be that first integral. You see it? That -1 to 0, because t equals -1 is up there at the top, and then 0 is here at the right. And so you give you all the area under the curve down to the x-axis. Now, what about from 0, t equals 0 now to 1.45? So that's going to be what? So now we're going to go from 0 to 1.45. So it's going to be all of this. But something's different here. What's going on? What happens to the x values as t goes from 0 to 1.45? What are the x values doing? Decreasing. So this will give what kind of value? It's going to give the opposite of that area because x is going to the left. You see? So when x goes to the right, that's our standard, integral. We get the positive area if the function is positive. But now x is going to the left as t goes from 0 to 1.45. So it's going to calculate that area, but it's going to be the opposite of it. So then what does the whole integral give? What does the whole integral give? So we got all this area for the first, and then we get the opposite of this area for that second part of it, 0 to 1.45. So can you see or describe what it's going to give?
The inside of the graph.
Yeah, so it's gonna give what's all inside there to the left of that line at x equals -3. So our integral from -1 to 1.45 is going to give all of that. It's going to be all that positive area minus, when it comes back here from 0 to 1, t equals 0 for 1.45, you're going to subtract all that. So this thing will be that region there. The area of that. Okay, does it make sense? And so then doing the math is just, taking q of t, which is your y function. You would take this y function here, multiplied by p prime, so 3t squared minus 6t. And so you would just have a long polynomial. You could do the antiderivative of that, and then take it for your limits from -1 to 1.45. So let's do that. Let the technology do it for us here. So what, -1 to 1.45. Okay, so what is q of t? Negative. Let me just copy and paste here. Doesn't like it. There we go. And then times 3t squared minus 6t. And then we want dt. 10.62. So that area of that shaded region there is 10.62 square units. Does that seem right? So we could just sketch 10 square units here. So 10 square units is like 2 by 5, right? So there's 2 by 5. That's 10 square units. Does it look a little bit bigger than that? it reasonable to think it's a little bit bigger than that? Yeah. Okay, so that's the idea of area, that when you're using these parametric equations, it's based on the area, the same thing we did before, y dx. So it's going to be from the curve to the x-axis. If t takes x in the opposite direction, those areas will get subtracted, right? So t here, 0 to 1.45, is taking x that way, so you get the opposite of that area. And then so the net effect of an integral like this would be to move everything inside the curve there, with negative 3 over. Okay, questions on areas? Okay, so let's move on to polar coordinates. So polar coordinates are based on is a different way of locating points in the plane. So what are we used to? We're used to x tells us how far left or right to go, and y tells us how far up and down to go. So polar coordinates are a totally different way of locating points. Instead of left and right and an up and down coordinate, you have distance from the pole is the origin, and angle theta, which is your trig angle swept counterclockwise from the positive x-axis. Okay. So here's an example. So as we sweep, let's see, does that show up? So as you sweep an angle counterclockwise from the x-axis, your point then is based on distance from the pole. So for instance, the angle right here is, this is the current angle. And then this is the point. So this then is the current distance from the pole, which we call r, like radius. And that gives you this point right here. So it's an angle and a distance from the origin. Straight line distance. So those two quantities together locate points in the plane. And so here is a polar function, meaning the distance from the pole is a function of what angle you're at. The distance from the pole, or this radius, radial length, is a function of what angle you've swept. And so this is kind of a cool one. So that was for theta going from 0 to 2 pi. I'll do it again, ready? So 0 goes from 2. So we're missing Andre for some, feedback here. I'm sure he would love this, right? Okay. So that was, you just saw the angle increase again from 0 to 2 pi, and then plot out all the points, distance from the pole for all those different angles, and that this forms this kind of cool butterfly-looking curve. Okay, so that particular function is this. E to the sine theta minus 2 cosine 4 theta. So a little bit more of a complex function, and that's why the curve is not real simple, right? But this is the kind of thing you get, things that are based on radial distance from the origin rather than rectangles, left and right, and up and down. My notes, here we go. Okay. Where is it? Okay, so let's just look at, this is pi over 4. So this right here, so this right here, so 1, 2, point there. Oh, I see. Okay. That's fine. Okay, so this is the point. Let's just do this one. So as we're graphing points, we label them as r comma theta. Okay, r comma theta. Again, r is radial distance out from the origin, which is called the pole. Okay, that's called the pole. Like if you're looking down on the top of the Earth, it's like the North Pole. Okay, so and you're looking, your r is your distance out. So what is r in this case for this point? 3. Do you see that it's on the third radius, a radius of 3 out, or that distance is 3, or it's on the circle of radius 3. And what is theta? Right here. Pi over 4. So this is the point 3 pi over 4. Okay, so this is the, so then for the angle pi over 4, this is the positive direction. Okay, pointing this way because this is the direction of pi over 4, pointing out this way. So then this is r equals 1, r equals 2, r equals 3, r equals 3.5, r equals 4, etc. So where would, for pi over 4, where would r equals negative 1 be? Where would r equals negative 1 be for pi over 4? What's that? Yeah, so here r is, these are positive r's getting greater, so then a negative r for the same angle pi over 4 would be here. So this would be the point. Negative 1 pi over 4. But then there would be another way to write that point. In fact, many other ways. What would be then another way to write that point? So here it's a negative r in terms of pointing in the direction of positive pi over 4. But how else would we write that point?
1, 5, 5.
He says he wants 1, 5 pi over 4. So which direction would 5 pi over 4 point? Would 5 pi over 4 point this way? Yeah, right, because this is pi over 4, 2, 3, 4, 5 pi over 4 would point this way. So this you could also write this as positive 1, 5 pi over 4. Do you get it? Both of those ordered pairs give you the same point in the polar plane. Okay, I want to make sure you understand that. Is everyone okay with that? You get it? Yeah. All right, there's another way we could write this. 1, comma, how about with a negative angle? With a negative angle would be, instead of sweeping counterclockwise, 1 and, so what angle is this? From here to here, if you swept it this way, be?
Negative 3 pi.
Yeah, that's what Patrick said too. Negative 3 pi over 4. So all three of those give that point. And then we could do 1 comma, and we could do 5 pi over 4 plus another 2 pi. So go around the whole, right? So if the angle was 5 pi over 4 plus another 2 pi, that would be another angle. So you could do 1, and how many pi over 4s is 2 pi? 8 pi over 4, so 13 pi over 4? Is that right? all those, and then there's an infinite number of ways to write any point in the polar plane. Does this make sense? Okay, so if we had the coordinates r3 or r pi over 4, what would the x and y version of that be? So what would the rectangular coordinates be for that point? Or how could you figure it out? What does x, so for that point right there, what does x represent? What is x? Can you explain what x is?
Is x the radius?
Is x the radius? No, x is the same as x for the last 8 years of your math career. What is x? Horizontal coordinate, right? It's a horizontal coordinate. So x would be like this right here. What does that horizontal coordinate equal? If we have swept pi over 4 and we're a distance of 3, then what is that coordinate right there? Something to do with cosine and sine, right? What would the y coordinate be?
Y sine.
Okay, it'd be that distance, right? So we should all know how to find those two quantities, x and y, if we've swept pi over 4 up and we're out 3, right? So this is pi over 4. And that right there is 3.
Three sine theta.
Okay, which is that, Kesman?
That's y.
Y. Y is 3.
Sine
We know what theta is. What's theta?
pi.
Yeah, and x is?
3 cos 5.
Okay, so those are both radical 2 over 2. So they're only the same because of the angle, right? Pi over 4. As soon as you have a different angle, x and y would be different. Okay, so in general then, what does x equal? Or we don't do that right now. Let's just a new picture. Does this make sense? So given r and theta, the question is, what is your x and y, the corresponding x and y coordinates of the point for r and theta? Based on a right triangle, right? So this is our point r comma theta. This would be x, this would be y. So x would equal r cosine theta, y equals. Okay. What is this length right here? It's r. What's another way to express that? Okay. So what's another way to mathematically express that length?
C squared or x squared plus y squared equals r squared.
Okay, so what would r equal? That's right.
So r would equal the root of r squared plus sine squared. Yeah.
Okay, and then this is theta. would be another mathematical way to represent theta. Another expression that would equal that angle theta.
Cos theta is all x over r.
What about the arc cosine of x over y?
Okay, so what about if we just wanted it in terms of x and y? So yeah, those are right, but what if we just wanted it in terms of x and y?
X and Y.
So what is theta in terms of x and y? So we've got what? Opposite over adjacent is equal to tangent of theta. So therefore theta equals? Anybody? If tangent of theta equals y over x, then theta equals arctan of? So these become our means of conversion. If you have the polar coordinate and you want the x and y, it's going to be r cosine theta, r sine theta. If you have the rectangular coordinate and you want the polar coordinates, r is going to be square root of x squared plus y squared. That's just right from the Pythagorean theorem. And then from right triangle shape, theta would be the arctan of y over x. Do all those relationships hold true if I pick a different point? Yeah, those are all identity type. So I still have, what, r and theta here? X is still going to be r cosine theta, y is still going to be r sine theta. That's still going to be square root of x squared plus y squared for the radius. And that's still going to be arctangent. Now we've got domain issues with arctangent. You have to know how arctangent works. Whenever you take an arctangent, you get an angle between negative pi over 2 and pi over 2. So remember, the range is negative pi over 2 to pi over 2. So may need to adjust. Because if you're over here in the third or fourth quadrant, you're not going to get the third or fourth quadrant, or second or third quadrant. You're not going to get a second or third quadrant angle. You're always going to get an angle between negative pi over 2 or pi over 2 when you take arctangent.
But it'll be like equivalent
Yeah, by symmetry. So you may need to adjust based on symmetry. That's right.
just by adding and subtracting.
Yeah. Okay, so this is our conversion back and forth between polar and rectangular coordinates. Okay, so can we do a quick exercise here, just to practice?
You can either take this point here
So I know it goes like
clockwise, so that's why I have
1, 2, 3, 4,
So we can take it from clockwise. So if you take it clockwise, you have to find the difference between
That's it.
5 to 5. So
That's the
that's
third point. So you're supposed to plot the points, right?
Yeah.
You're plotting points.
5 minus
This is a point in the plane. This is a point in the plane. So
5 minus
the first thing is to plot the points. Find the exact location of those ordered pairs.
So that's how
From knowing it.
I can draw the circle.
well,
That's what I'll do.
Okay, which one should I do?
Because sixth. Sixth and draw
because
whichever way you do it.
see how this is?
Or you're gonna do this
One.
Wait, which one should I do? Should I do?
From
So this is like
Yes.
number 2 or number 3?
Two.
2? Number 2. Okay, so first we got to determine the direction of the angle negative 2 pi over 3. What's the direction of the angle negative 2 pi over 3? What quadrant is that in? Third quadrant, right? So instead of going, so positive is going this way, so negative going this way, and then 2 pi over 3 would be? Oh, why? So I'll just do it here. It's because my screensaver went on, that's why. Okay, so 2 pi over 3 is, this is not the right thing. It's like right here. How's that showing up? I don't know what's not showing up. I don't get that. Alright, I'll just try to draw it here. It's something like this. That's the direction of negative 2 pi over 3. It's that angle right there. Okay, and then what was the coordinate? 2. So we're gonna, this is the, whatever angle you're given, that's the direction of positive r. That's the direction of positive r. So we're just gonna go a distance of 2 from the pole.
What's the pole?
The origin. Okay, so then, and then the part 2, I asked you to write that point in polar coordinates 2 other ways. So this is the point, 2. So what's another way to write that point? What's that? All right, so he wants the angle, if there was the angle pi thirds, that would point in this direction.
So positive 2 pi.
So that's the angle pi thirds. So what? Yeah, so this is the direction of positive r. So then if you had negative 2, it would take you back here. That's right. Okay, what about an angle like this? Know what that angle is?
4 pi over 3.
It's 4 pi over 3. So what would the r value be if we use the angle 4 pi over 3?
Is it positive 2?
Positive or negative?
Well, positive 2.
Positive 2. So all 3 of those are ways of writing that, yeah?
How do we know that an ordered pair is a polar coordinate?
Because I told you, I said write them in rectangular coordinates, and then by context, these are all in pies. So I said write these coordinates as rectangular coordinates.
I get it in this context, but like if I just saw that, that could be Cartesian.
You just have to look in the card. Yeah, you said it. Yes, you'll know by the context.
Okay.
It would tell you, or it would just be clear. But yeah, it does look. They look the same. Just if this was just floating in space, you wouldn't know. It certainly you would guess it's polar coordinates,
Yeah, safe to assume.
but it's no, it's not safe to assume. But that would be your guess. That'd be your guess. But you need context, or they need to tell you. Yep. Other questions? Okay, so we want to talk about polar graphs. Polar graphs. So let's look at. r equals 2 sine theta. So this is, what we've got is r is a function of theta. So theta is input, and then r is output. So given this relationship gives us a distance from the origin or distance from the pole for every given angle, right? For every given angle. So the only thing that's a little counterintuitive then is, but points are this way. So points are listed as r theta. But in these polar graphs, that's the output, okay? So just be aware of that. And that's the input. So that's reverse of what we're used to in x and y, okay? So just be aware of that. Okay, so in order to make a sketch of this, what we need to do is we want to sketch this in Cartesian coordinates first. And so you have to, this is where a lot of students have trouble because they've forgotten how to sketch trig graphs. And you need to sketch that trig graph first correctly in order to then sketch the polar graph. Okay, so our input is theta, and output is r. So we're gonna plot r equals 2 sine theta in rectangular coordinates. Theta is on our x horizontal axis, and r is going to be our y, like our vertical axis. And we should be able to, it's a real easy one, we should be able to sketch 2 sine theta. And then from this graph that we make in rectangular coordinates, we're going to go and figure out what it would be in polar coordinates. Okay, so what is the graph? What is the sketch of the graph of 2 sine theta? Can you do it? Do you know the period? Do you know the amplitude? Do you know the pattern of 2 sine theta? Let's start with the period. What's the period? How often does it repeat? Good, 2 pi. So let's just start by trying one period of this. Okay, 2 pi. What about, we know it's cyclic, and it's the shape of a wave. Do we know the max and min of 2 sine theta? Okay, good. 2 and negative 2. And so we've got min, midline, and max. And we break it up into 4, basically there's 4 parts to the cycle. So pi over 2 pi, 3 pi over 2, 2 pi. And then in each one of those 4 parts, it's either going to be at the midline, the min, or the max. So sine theta, does it start its cycle at 0 at the min, the midline, or the max? Midline, right? So start at the midline and go where from there? To the, in the first quarter period, up to the max or down to the min? Back to the midline, down to the min. So these, you got to be able to sketch these graphs, and harder ones than this. Okay, that's an easy one. So we're going to look at this. How does r vary with theta? And we have to apply that to the polar plane, with r being distance from the origin and theta being our angle swept counterclockwise. So here we are. Theta equals 0, which would point out here the x-axis. What is our value of r? 0. So we start at the pole, 0, 0. Okay, so what happens? As theta goes from 0 to pi over 2, what does r do? So as theta goes from 0 to pi over 2, according to 2 sine theta, what does r do?
Is from 0 to 2.
He wants it 0 to 2. Agree? Yeah. So you got to imagine that as we turn our angle, is that showing up? Okay. As we turn that angle from 0 to pi over 2, what is our distance from the pole going to do? going to increase from
0 to 2.
0 to 2. So when I get to pi over 2, we know that when I get to pi over 2, here, where am I at? What point do I have?
2.
2. Here's the point, pi over 2, 2. So the question is, what does it look like in between? So with each increase in
Like a swoop.
so with each increase in angle, so I'm just guessing here, but so like you're gonna get some distance for this angle, and then when you increase the angle, what you're gonna be now a greater distance farther, right? And so with each increase in angle, oops, we're going to get, so for each increase in angle, we get farther and farther until it increases from 0 to 2. So do you see it for these increasing angles? I'm making r greater and greater until you get to 2. See that?
And the rate will decrease as you increase the angle?
Yeah, right. So it will get further from the origin at the fastest rate here at the beginning, and then slower. Yeah, good observation. That's good. So maybe I didn't get it out fast enough here at the beginning.
Like whip around and level off.
Yeah, so it's going to whip out fast at first, and then it's going to slow down. Something like that. Okay, and then what happens then from pi over 2 to pi? What happens to the value of r? So as we go from pi over 2 to pi, so here's pi over 2, and then as we go to pi, what does r do? Back to 0. So we're going to start at this point, and as we go through the second quadrant, we're going to be back at this point, and what will those values of r do?
They're going to decrease.
Decrease slowly at first, and then more quickly. So they're going to decrease kind of slowly here.
Is it just going to be like the inverted reflection?
Yeah, so then it's going to be basically, and then much more rapidly, right? Okay, next, from pi to 3 pi over 2, what does the values of r do? From 0 to negative 2. Where is the point 3 pi over 2, negative 2? So it's going to be goes from 0, but then these r's are going to go, it's going to be negative r's to negative 2 as we sweep through the third quadrant.
It's just going to retrace what we already had.
Where? Yeah,
The,
which part?
like the part that we already outlined, it's just going to retrace it, right?
The whole thing?
Right.
When we're in the third quadrant? For this angle here, I'm going from pi over 2 to 3 pi over 2. So when we go from pi to 3 pi over 2, r goes from 0 to what? Negative 2. So what's going to happen? Where's 3 pi over 2, negative 2? Here's 3 pi over 2. Where's negative 2?
It's at the top.
At the top of the circle. You all seeing, looking at that? Thinking that? Not saying it though?
Yeah.
This is this point. Negative 2, 3 pi over 2 is this point. So what are we going to do? We're going to get quickly negative and then more slowly negative as we transverse through the third quadrant, which is the same as what?
The second quadrant.
No, not the second quadrant.
How about the first?
Which is it?
The first.
Yeah, so if this angle is increasing and we're increasing negative, we're going to just repeat this. Do you see that? It just repeats that thing right there. And now we're at negative 2, and we're going to go from negative 2 to 0 in r as we sweep from 3 pi over 2 to 2 pi. And that's going to do what?
Taking back to 0.
It's going to retrace this. These are all the negative values of r for the fourth quadrant. So this one period of pi actually makes 2 cycles of this graph. You only need pi to get the full graph. Because from pi to 2 pi, it's going to repeat it again as the negative values of r through these angles here. Do you see it? All right, so
How do we know that without mapping the whole original period? Is it because it's reflected about the x in the Cartesian?
okay, what's the question?
How do you know the period of a polar curve based off of the period of the Cartesian?
You have to graph them all. They're all, there's
You have
no,
to do them all?
yeah, there's no, you can't just do each one at a time and then make that conclusion when you're done.
Okay.
Yeah. Okay, but so are these the only points on the graph?
That's every.
Yeah, this was just kind of our getting the idea. So what do we think? So something like this, right?
Isn't it kind of like a heart? It isn't pinch-off in the middle?
Okay, so let's have the technology do it and see what we got. Okay, so we know it's something like this. I'm gonna erase. Can I erase everything I've drawn on the screen?
Yeah.
You good? So what do we do? 2 sine theta. That should. Did I have it turned off though? Here we go. Ready?
Oh, it's just a circle?
Sure looks like it, right?
It's a circle.
But how do we do? I mean, in terms of making a sketch, we do okay?
Wow.
Okay, so let's prove that it's a circle. We can prove that this is a circle by taking this equation and changing it into x and y. Get rid of r and theta and change it into x and y. How are we going to do that? Okay, yeah, we could do that. But let's see, we got 2 sine theta. It would sure be nice if we had what on the right hand side instead of 2 sine theta? We're changing this into x and y. Sure be nice if we had. Okay, what does x equal and what does y equal?
R cosine.
Okay, and y equals? Now, what do we have? On the right, we have just sine theta.
Oh, we can multiply.
It would be sure be nice if we had what?
R sine theta.
R sine theta. Would it be nicer if we had r sine theta?
Now it's all the radius. Never mind.
So if we want, it would be surely nice to have this, right? Can we? Can we just change that? Well, we got an equation. What equals 2r sine theta? Yeah, 2y, but according to this, what does 2r sine theta equal?
R squared.
R squared. Right, you just multiply both sides by r. Okay, so we got y here. 2y, sorry. And what's r squared? X squared plus y squared, right? Okay, so we see this is a circle, but it's not the form that we're used to, so we can do 2 minus 2y. And then we need, what we want is perfect squares, right? Because what's our equation of a circle? X minus h squared plus y minus k squared equals r squared. So what? We need to complete the square. How do we complete the square? We take half of that and square it. What do we get? Half of that b value and square it. Plus 1, but then we got to add plus 1 over here. So then we got x squared plus, this is now a perfect square. What perfect square is it? y minus 1 squared. So that's a circle with center. What's the center? 0, 1, radius.
1.
Oh, you mean this circle? Center. 0, 1, radius. 1.
But we can only do this R business because it is a circle, right?
What's that?
Like the multiplying by R to get R squared.
It doesn't have to be a circle. We could still use that technique to get a y.
Really? I thought we were relying on the formula for a circle that x squared plus y squared equals R squared. Oh no, that's the definition you gave us earlier. R equals square root x squared plus y squared.
Yeah, so ours, the distance from the pole by the Pythagorean theorem is square root of x squared plus y squared. So the Pythagorean theorem is literally r squared equals x squared plus y squared.
Gotcha. That makes sense. Thank you.
Okay, so when we sketched it, we got that circle, but then this proves that algebraically by changing it from r to sine theta into its equivalent. So these are equivalent. We did the algebra to show it. That right there is equivalent to that. So their graphs are the same. So this, what we sketch when we sketch this, we sketch the graph of this circle, the blue circle right there. Center 0, 1, radius 1. Okay, so let's try a different one. Well, we got a couple minutes. Here we go. Let's try 1 minus cosine theta. Can we sketch it in the Cartesian plane? Should be able to. What is the period of 1 minus cosine theta? 2 pi still. Okay. Where is the max and the min? So this is really like negative cosine plus 1. That's really what we're graphing. Okay, so max and min of this.
The minimum point is 0.
Yeah, so we're taking cosine theta, we're moving the whole thing up 1. So the min is going to be at 0 now, and the max is going to be at 2, right? 2. And our midline, 1. Okay, now so again, we're going to draw one period of this. Negative cosine is going to start where? At the min, the midline, or the max? So we've got to know where cosine starts. Cosine starts at the max, so minus cosine is going to start at the min. And then we're going to go up to the midline, and then up to the max, and then back to the midline. So these are the graphs you need to be able to sketch. Okay, better. Something like that. Okay, here we go. So at x equals 0, or sorry, from 0 to pi over 2, what does r do?
Increases to 1.
Increases to 1. So we're thinking about sweeping the angle theta from 0 to pi over 2. R is going to increase from 0 to 1. Something like this. And then, as we sweep from pi over 2 to pi, r goes from what to what?
1 to 0.
1 to
1 to 2.
2.
Or 1 to 0.
So at pi, we're at positive 2. Again, more quickly at first, and then slowly at the end. Okay? And then, from pi to 3 pi over 2, radius goes from? So here's from pi to 3 pi over 2. We're going to go back to 1. Okay? And then back to 0. So as we go from 3 pi over 2 to pi,
Oh, this is the hard one.
yeah, let's see how we did.
Oh, good. Oh, that's something like chord.
Cardioid.
Cardio.
Ready? Here we go. Maybe? Oh, I didn't turn it on. There we go. Let's make it blue. Green doesn't show up, it's too light.
Nailed it.
Almost, almost, come on, help me. There we go.